Okay, so in this module, we're going to be talking about logarithms. So earlier we were discussing exponentials, and what you see in front of you here is an exponential function, y equals b to the x, right? And has a y-intercept at the coordinates 0, 1. Now this graph of the exponential is a one-to-one function, which means that it has an inverse. Right? And the way we can find the inverse, at least graphically, is it's reflected across this line y is equal to x. That's the line we see here. So its reflection, right, we'll see, all right, this would reflect to the point 1, 0. Right? And instead of having an asymptote at the x-axis, the asymptote will now be the y-axis. Right? And it'll look something like this. All right, and this function, y, which is our inverse exponential, this is what we call a logarithm, right? So we define the logarithm as an inverse of an exponential function, right? So in general, when algebraically at least, we use this notation here, y log base b of x, right? Is how you pronounce this statement here, log of x. All right, and that is defined as, right, this is true, this statement is true if and only if this exponential is satisfying, right? The base of our logarithm is the base of the exponent, and the exponent is now the value of y, or the output of the logarithm, right? So really the way we can think of a logarithm is as a exponent of some exponential. Okay, so the input, right, would be the result of this exponential that we have here, and the result of that would be the value of the exponent. Okay, now it is an inverse, right? So when we have, for our exponential function, the domain was all reals. So for our logarithm, the range is going to be all reals. Right? And here the domain, right? If you notice here, the range for our exponential was 0, all positive numbers, right? So we don't include 0, so now our domain becomes that, 0 to infinity. Okay, now there's no, the exponential and the logarithm are what are known as transcendental functions, in the sense that they kind of transcend algebra. So there's no like algebraic operations where we can get from one to another. This is just how we define these functions. Okay, and as we'll see later when we get into properties of logarithms and even the exponential properties, right? Those aren't like algebraic properties that we are used to working with, right? So they have their own operations that we kind of use to work with. Okay, now things that are useful, just the Richter scale, right? Even in California is something we're probably familiar with. Is something that works on a log scale, right? And the reason for that, it's when we have a wide range of values, it's easy to represent using the log scale. So if you jump from, instance, a magnitude earthquake of 3, 4, while it only seems it went up 1 unit, that's actually an increase in 10 times the magnitude of the seismic waves, right? So these using the logarithmic scale is good for representing values that have a wide range of values that it can take on, and you can represent them easier in a way that can be more easily interpreted. All right, thank you.